Right, here we go. So welcome to today's first stream of the year, and we're doing sheet 12 from our A-level series. And here's question 1. I'm just going to give you, I think I'm going to give you 3 minutes to have a go at this and see how you get along. Right, hopefully that was enough time. So if we want to show that if y equals sec to the nx and dy by x equals a y tan x, the first thing we are going to do is we're going to try and just see how to differentiate y equals sec nx. Now, you should begin to this stage of the course where you can do chain rule problems in your head. So what we're going to do is we're going to differentiate the sec. Now, we know that sec goes to sec x tan x, and then we're going to get n coming down to times by that. So we're going to get the divided by the x, we times by the n, and the sec x goes to sec x tan x. And then we're going to take 1 off this power, so as we get sec the n minus 1 x. And what you see is we get n tan x sec. Now we've got sec x times sec to the n minus 1, which is just going to be sec to the n x. And we want to show that dy by x equals a y tan x. Well, y is sec n x, so we've got the y there. So we've got n y tan x, which we can just write as a y tan x, because n is just a constant and a is just a constant, so therefore it's the same as a y tan x, where a equals n. Now, if we want to integrate tan x sec the 5x dx. And this is just reversing this process. We can see that this must come from just sec to the 5x as a power. And what we don't have is, we don't have 5 tan x sec x, so therefore we need to do 1/5 of that and add a constant. Now if we want to integrate cot cosec to the 4x, then we need to remember that the derivative of cosec x is equal to minus cosec x cot x. So if we know that it's come from minus cosec x cot x, then we can see that the integral of cot cosec 4x dx is going to be very, very similar to this question here. So we can see that we've got this differentiating, so this is going to come from cosec to the 5x. I just realized, so this is going to come from, cosec to the 4x, because we've got the cosec cot coming out when we take off the powers. Exactly the same as the question, except the sign changes. This must also come from cosec 4x. Let's see. We've got a minus, change of sign, so we need a minus, and we're also going to need a quarter in there. Right, next question. Yeah, question 2. Off you go. This one's a little bit longer, so I think we'll give you, let's just check. I think this would be a 5-minute question, so timer for 5 minutes. Just going back to the Formosa 2, if you can remember from the previous questions, the initial velocity in that was 25 meters per second. And for part C, we're using 125 meters for the maximum height. 1 minute to go. Okay, hopefully that was enough time. So what we need to do is first of all sketch a graph of the rocket's velocity against time t. So we're going to draw this, and we've got the velocity on this axis and we've got the time on this axis. And what we can see is we've got a sort of 1 over x type graph where if at t equals 0, we can see that the velocity is going to be 25 and it's going to be decreasing because as t gets bigger this is going to get smaller over time. So it's going to intersect at 25 here and it's going to get smaller over time. So therefore part B, when t equals 0, v must equal 100 over 4, which equals 25 meters per second. Now we want to find the distance it travels in the first 5 seconds. So in the first 5 seconds it will travel, integral from 0 to 5, 100 over t plus 4 dt. So we integrate that and we're going to get 100 natural log of t plus 4 between 0 and 5. That's going to give me 100 times the natural log of 9 minus 100 times the natural log of 4. So it's effectively 100 natural log of 9 over 4. Take 100 out as a factor. Natural log of 9 minus natural log of 4 is natural log of 9 over 4, which comes out to be 81.09 meters. Now, we want to find the time of the Formosa 4 passes the maximum height reached by the Formosa 2, which is 125 meters. So we're going to integrate from 0 to the height, we're going to call it x, 100 t plus 4 dt, and we're going to make that equal to 125. So therefore we put 100 natural log of t plus 4 between x and 0 is equal to 125. Give myself a bit more space. So what we put the limits in, 100 natural log of x plus 4 minus 100 natural log of 4 equals 125. And we can divide that by 100 and that will give me, and then take these two by, let's just divide by 100 so don't see too much working in one go. And you get 1.25, and then we combine these two to get x plus 4 over 4 equals 1.25. Raise both sides to the power of e, we get x plus 4 over 4 equals e to the 1.25. So we can see that x is going to be equal to 4 times that minus 4. 5 minus 4, which comes out to be about 9.96 seconds. Right, next question. Question 3. Let's see how long we should give you this. I think this is a much more straightforward question. You're either going to get it quite quickly or you're not. So I'll give you 2 minutes to have a go at this one. Right, sorry about that. The logo was covering up some of the question. So we're trying to describe fully that either there's two single transformations which maps this curve onto this curve. Now the best thing to do is what we're going to do is we're going to just try and rearrange this one so we can work out what this curve is. Now what we can see is it's got something similar to do with circles. So let's try completing the square for this. So we get x minus 3 squared. Now that will give me the x squared minus 6x, but it will also give me a plus 9. So I'm going to minus 9 from that. And then I'm going to get y minus 2 all squared, which I'm then going to take off the 4. And then I've got this plus 9 on here to add in that. I think it's a good habit just to make this equal to this and this equal to this, and then have any extra numbers added on the end, and you don't make any mistakes. It's always a good idea to take away the number on the end squared to match up the y's, the number on the end squared to match up the x's, and then you can just add in any extra numbers. And we can see that these 9's cancel. So we've got x minus 3 all squared plus y minus 2 all squared equals 2. So we've got a circle, centre 3, 2, radius 2. And then if we do the other one, so we do x squared minus 18x plus y squared minus 12y plus 81 equals 0. X squared minus 18x, that's going to come from x minus 9 all squared. Take away the 9 squared, it's 81 plus y minus 6 all squared. Take away the 6 squared, that gives me minus 36. And I've got a plus 81 here, so just like the last one, it's going to cancel. So we get x minus 9 all squared, plus y minus 6 all squared equals 36. And I just made a mistake. That wasn't 2. That should have been a 4 there. Okay, I was thinking of 2 squared for the radius. So this, we draw this. So we've got the first one as a circle radius 2 going through the point 2, 3. That's not very well drawn, is it? Just try and change that slightly. It doesn't actually touch the y-axis, so it goes through the point 2, 3. And the next one is a circle radius 6 going through the point 9, 6. And I've got this one wrong way around. That should have been 3, and that should have been 2. Actually, I've got the circle's orientation correctly. I just haven't put the x-axis right. So what we've got is you can see the center of this circle has moved from 3, 2 to 9, 6. That distance has increased by a factor of 3, and this distance has increased by a factor of 3. So what we have, and this has a radius of 6, and this had a radius 2, so the radius increased by a factor of 3. So what we have is an enlargement, scale factor equal to 3, center 0. So the next question. Question 4. Quite a straightforward one. I'm not going to give you very long to have a go at this. I'm going to give you just 60 seconds to see if you can pull this one out. It shouldn't take very long at all because you should know it off by heart anyway. So here you actually not 60 seconds. Okay, and then you can see the proof. Right, here we go. So what we're going to do is we're going to let a equal b equal theta. So let's have cos of theta minus theta is obviously naught. And put that into the addition formula. So we get cos of theta times cos of theta plus sine of theta times sine of theta. Cos of theta minus theta, that's cos of 0, and cos of 0 is equal to 1. Cos times cos equals cos squared theta plus sine squared theta. Now, to prove these two remaining Pythagorean identities, what we can do to do the first one is we can see that tan squared is just sine squared over cos squared. So we divide each term by cos squared theta. Like so. Divide each term by cos squared theta. So I can see that this is equal to sec squared theta. This is equal to 1. And this is just equal to tan squared theta. Sine over cos is tan. Sine squared over cos squared is tan squared. And similarly, for the next bit, what I'm going to do is I'm just going to divide everything by sine squared theta. So I get 1 over sine squared theta equals cos squared theta over sine squared theta plus sine squared theta over sine squared theta. So that implies cosec squared is equal to cot squared. This is cos over sine, which is 1 over tan, which is cot squared, and that's just plus 1. So we get our 3 Pythagorean identities, which you need to know. Right, our next question. Question 5. And this isn't a long question either. We'll give you 3 minutes though to give you some thinking time as well. Right, so we got line L1 lies tangent to y equals a half x, and x is pi over 3. By an exact form, the places where L1 meets the x and the y axes. So first of all, we need to find the tangent. And to find the tangent, we need to find the gradient. So we're going to take, sorry, I've still got the highlighter selected. Let's just undo that. And get a pen. So y is equal to tan x over 2. So dy by dx is equal to a half sec squared x over 2. Got the half coming out from the x over 2. At x equals pi by 3, we've got dy by dx will equal, so we've got x divided by 2, so we've got pi by 6. So we've got sec of pi by 6, and a sec equals 1 over cos. So cos of pi by 6, if you remember, cos is up here, so it's going to be root 3 over 2 for cos of pi over 6. So cos of pi over 6 is root 3 over 2, and we've got 1 over that, so we've got 2 over root 3. We've got square that, that's 4 over 3, and then we've got times that by a half. So we've got a half times 4 over 3. So that leaves us with 2/3. Okay. And we know that the y value, if we put pi by 3, so we get pi by 6, tan of pi by 6 is 1 over root 3. So therefore, using y minus y1 equals m times x minus x1, where m is the gradient, y1 and x1 is a point on the line. We get y minus, our y1 value is 1 over root 3. Our m value is 2/3. X minus our x1 value is pi over 3. We could try to simplify this much, but I don't see that it's really going to do as much good, so I'm going to leave it as that. Anyway, we want to find out where it meets x. So it meets x, where y is equal to 0. So we get minus 1 over root 3 equals 2/3 open brackets x minus pi over 3. So we can times that by 3 and divide by 2. So 3 divided by root 3 is root 3 divided by 2. So it's going to be minus root 3 over 2 equals x minus pi by 3. I'm just going to go up here to finish off the working to keep it all on one screen. And so therefore we can see that x will equal pi by 3 minus root 3 over 2. And where x equals 0 is where it meets the y-axis. So we're going to have y minus 1 over root 3 is equal to 2/3 times 0 minus pi by 3. So y minus 1 over root 3 will equal 2/3 times by this. So it's going to give me minus 2 pi over 9. So y will equal 1 over root 3, and you might prefer root 3 over 3 to 1 over root 3, minus 2 pi over 9. We could write this as a single fraction, times that by 3, divide by 9, and write 3 root 3 minus 2 pi over 9 if we wanted. So we found out where L1 meets the x over here, and where it equals the y over here. Right, our next question. Okay, differentiate this from first principles. I'll just give you another couple of minutes to have a go at this one. Right, here we go. So we want to differentiate this from first principles. So we're going to let f of x equal 4x squared minus 3x. So therefore f of x plus h will equal 4x plus h squared minus 3x plus h. So f dashed of x will equal f of x plus h minus f of x all over x plus h minus x. So f of x plus h is equal to all of this. So let's just multiply this out while we're doing it. So we get 4x squared plus 2hx plus h squared minus 3x plus 3h. And then we're going to take away from that f of x, so we get minus 4x squared plus 3x. Minus and minus will give me a plus. All over, take away the x's, h. So that's going to give me 4x squared, which is going to cancel out the minus 4x squared. So I'm going to get 4 times 2hx, which is 8hx. 4 times h squared plus 4h squared. Minus 3x is going to cancel out with a plus 3x to leave me just plus 3h all over h. And we can see we can cancel out an h here, an h here, and an h here, and an h here. So if I take out h as a factor, then cancel it, I can cancel that down. And that will leave me 8x plus 4. Therefore, I seem to be missing something. Plus 4h plus 3. I knew there was something missing because there's always an h somewhere that we need to get rid of. And so therefore, as h tends to 0, f dashed of x will tend to 8x plus 3 is our answer. You've got to always have some, there's always going to be an h here that you have to eliminate by allowing h to tend to 0, and then f dashed of x will tend to the derivative. Okay, that's how we do differentiation from first principles. Right, our next question. Question 7. Hopefully you'll spot, this is us beginning to start the journey on deriving Maclaurin's theorem. Over the next few sheets, you'll see it being built up gradually over time. And those of you who already know how to do Maclaurin's theorem should find this quite straightforward. I'll give you 3 minutes to have a go at this one. Right, for our last question. So what we need to do is we need to differentiate f of x several times. So f of x is equal to cos x. F dashed of x is equal to minus sine of x. F second derivative is going to be minus cos of x. F triple dash, or triple prime, or whatever you want to call it, is going to be sine x. And the fourth derivative will be equal to cos of x. So we can now find f of naught, which is just 1. Cos of 1 is 1. F dashed of naught is equal to sine of 1, which is 0. Sine of naught, which is 0. F double dash will be minus 1, because cos of naught is 1 minus 1. And double dash will be naught. Sine of naught is naught. And the fourth derivative, cos, is going to be equal to 1. Now, you may not see easily how to work this out, and this is not really that important for when we're coming onto Maclaurin's, but if you want to work out, you may realize that what's going on is we're going at f dash, at the first derivative, we're going at 1, and then we're going 0, and then we're going minus 1, and then we're going 0, and then we're going 1. And what you may have noticed is this looks just like a cos curve. So therefore fn of naught would equal cos of pi by 2 times by n. So if when n is 0, cos of pi by 2 times n is equal to naught. Cos of naught is equal to 1. And then you notice the next term, naught, is pi by 2 along. When you go on the cos curve, and another pi by 2 along, and you can see why it's cos of pi by 2 n. This is not that important when working out Maclaurin's. This is going to be the important bits. Knowing that you differentiate each term, you put 0 in, and you get the coefficient out. And eventually we'll come up with a formula in a couple of sheets' time. Anyway, that's the end of today's sheet. Will be another one tomorrow at the same time. Hope that was helpful, and see you then.